Welcome back. We discussed discussing binary cubic quadratic form, and we what we saw last time. Uh, so what we saw last time is that on the set of binary quadratic forms, integral binary quadratic form, there's the equivalence relation that if f is equivalent to g, there is a SL to Z matrix. So SL to Z is the 2 by 2 integer matrices, integer coefficient and determinant 1. And if there is a matrix such that the matrix of the binary quadratic form F using that matrix can be transformed to another matrix. So more precisely, if the matrix of F is, let's say, A, which is A B by 2 B by 2 C, and if there is a Q transpose AQ is the matrix of G. So G X Y equal to so X Y transpose X Y. Then where A is A B by 2 C by 2, and this Q is the 2 by 2 integer matrix with determinant 1. Then we call G to be equivalent to F, where F is F of XY is XY transpose A B by 2 B by 2 C and XY. Then if this happens, then we call F and G to be properly equivalent or SL to the equivalent, and this was an equivalence relation on the set of binary quadratic forms, integral binary quadratic form, which are primitive and have a given discriminant. So under this equivalence relation, the discriminant doesn't change, and moreover, if the form is primitive, it remains primitive. If a form is positive definite, it remains positive definite. So we consider the set of equivalence classes. So this is an equivalence relation, and the equivalence class is a unique. Every equivalence class is a unique member which is reduced. That means so this binary quadratic form is said to be reduced if mod b is less than equal to a, less than equal to c. You arrange it in this way, and if there is equality at this stage and this stage, then b is equal to a, mod b equal to a. Then if this equality holds or this equality holds, then b is positive, non-negative. Okay, so the example is x square plus ny square, x square plus y square, and so on. So what we proved last time is that so then the statement I said that every equivalence class contains one. So you fix a discriminant delta, and every integral binary positive definite binary quadratic form is equivalent to a unique reduced form of discriminant equal to delta, and any two reduced binary quadratic form, positive definite and primitive, are not equivalent to each other, properly equivalent to each other. Okay, so and the proof, we omitted the uniqueness, and then last time we showed that the number of equivalence classes is then the number of reduced form is the same as the number of reduced form of a given discriminant. So the number of equivalence classes of primitive positive definite integral binary quadratic form of given discriminant is finite. And so basically you have to prove the number of reduced binary quadratic forms, number of positive definite primitive reduced binary quadratic form of given discriminant is finite. And the way we proved it is simple calculation using the properties. Okay, so so then we say that we said that there is a group structure on this set of this equivalence classes of binary quadratic form. These are called Gauss decomposition law or Dirichlet decomposition law, but we are not going to discuss this in this course due to lack of time. But what we did say is that so this will not only, it's a finite set, it will become a finite abelian group, and the goal is to give a bijection from this set to if you start with the imaginary quadratic field, then we have discussed the equivalence classes of ideal class groups, and so there's a bijection from this set of equivalence classes of binary quadratic form of discriminant delta, where your imaginary quadratic field Q root delta and there's a bijection, so the class number is finite and the number is equal to the number of basically reduced binary quadratic forms. And and in fact, it's a group isomorphism, but we are not going to discuss it. And this is quick recall of fundamental discriminant. If Q is of the form Q root delta is the imaginary quadratic field, delta is less than 0, and delta is called fundamental discriminant. It is the discriminant of the ring of integers of K. So delta is either 1 mod 4 and delta is square free, or delta is 4D and D is square free and D is 2 or 3 mod 4. Delta is less than C. Okay, so the map was the equivalence class of integral positive definite primitive binary quadratic form of a given discriminant from given discriminant delta. So two forms are equivalent if their matrices are related this way. This was X transpose AFX, where AF was a symmetric matrix. So AF was equal to A B by 2 C by 2 and A B by 2 B by 2 C, and B then is given by Q transpose A G Q, and the binary form quadratic form was AX square plus BX plus CY square, the discriminant delta. Then this is set to the ideal. So ideal Z. So so on the right hand side we had the equivalence classes of ideals and set of ideals, non-zero ideals I and J are non-zero ideals in O delta, and I is equivalent to J if there exists alpha beta in the ring of integers, both of which are non-zero, so that alpha times I equal to beta times J. Then on the binary quadratic form X square plus BXY plus CY square B square minus 4 is equal to delta, you send it to IF, the ideal generated by A and minus B plus root delta by 2. But what do you mean by ideal generator? This is actually, you define it to be the abelian group generated by A and this turns out to be ideal. It's an ideal inside IF, inside the ring of integers, and you look at the equivalence class of this ideal. So you get, this is the map, and I'll prove this map is well defined, surjective and injective. Well defined and surjective means because this side it's finite, that this class group is finite, and injective means that the cardinality are the same, so you can count the number of reduced binary quadratic forms to get the number of the class number of the imaginary quadratic field. So actually the inverse map also you can write down. Suppose I is an ideal, then it's a free abelian group of rank 2, rank at most 2, so that's generated by alpha and beta as an abelian group. Then you send it to the binary quadratic form fxy, whose value at xy is norm of alpha x plus beta y divided by norm of I. So you can show it's an integral binary quadratic form and the discriminant is delta. So this will be the reverse map, but we'll use this reverse map only in the surjective step. So we'll go with this side in the map. So there are 3 steps, as I said: well-definedness, injective, and surjective. Okay. So let me go through the precise detail now. And so first of all, let us define the map again. So I briefly outlined it. So on integral primitive positive definite binary quadratic form fxy ax square plus bxy plus cy square, and the discriminant delta b square minus 4 is negative. You take q root delta. On that you define if to be za plus z minus b plus root delta by 2. Okay, so you have ax square plus bx y plus cy square, and you take this abelian group generated by a and minus b plus root delta by 2. So this is all the set m times a plus n times this, where m and r is z. So first of all, you note that in this case, because delta is a fundamental discriminant, we have chosen delta in this way, that delta is a fundamental discriminant. So the ring of integer is given by z delta plus root delta by 2. So this was one of the exercises you may recall. So it is r plus s times delta plus root delta by 2, where r, s are in z, right? This is that set. And so the claim is that this if is an ideal. So first of all, you make some observation that delta plus root delta by 2, you just literally write it down, is b square minus 4ac plus root delta by 2. But b square minus 4ac and b has the same parity, right? Because this is even So I mean, so this can be written as so b square and b has the same parity. So minus b also has the same parity. So this can be written as minus b plus 2m uh, 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 by root delta. So just think for a moment, plus root delta by 2. So this is equal to minus b plus root delta by 2 plus some integer m. And this shows that, so this shows that delta plus root delta by 2 belongs to this z minus b plus root delta root delta by 2. Okay, so you, if you define omega f to be this minus b plus root delta by 2, so this is an element of O delta, right? Because this is an element of the ring of integer, so this is in ring of integer, and in fact z omega f, then minus b plus root delta by 2 is omega f from this step, right? You look at here. The ring of integer is given by z delta plus root delta by 2, and delta plus root delta by 2 belongs to this abelian group. So, and obviously this is a subset of this, so this is an equality, right? So then what I have defined if, so first thing is O delta is the ring of integer is given by z times the free abelian group then by z omega f. So this is equal to m plus n omega f, where m comma n are in z, right? So this is O delta. Then if is a. So what was if? So this is equal to, you recall, this is equal to z a plus z omega f by definition, right? So this is inside this, and to show that this is a subset of this, it's an abelian group inside this, and to show it as an abelian ideal, you have to show that O delta times if is contained inside if, so z times omega f is contained inside itself, but it's an abelian group, so it suffices to show that omega f times if is contained in this. But again, by definition, if is a times omega f is already there, so it suffices to show just omega square belongs to I by the definition of I. So think about it for a moment. So you just need to show omega square f. Now what is omega f? Let's just calculate this thing. So omega f is minus b plus root delta by 2. So this implies that omega f square is b square plus delta minus 2b root delta by 2. So this implies this is equal to uh, yeah, so this is equal to b square plus delta. Uh, so yeah, so this is b square equal to, so uh, b into so I want to say that this is in yeah, so I want to write it as, so let's just write down what is, yeah, so this is equal to b square plus b square minus 4ac minus 2b root delta by 2. So this is some b square minus 2ac uh, yeah, minus b root delta. So uh, so just a moment. So b square plus delta minus 2b root delta. So this is b square plus delta is b square minus 4ac. So yeah, so 2b square minus 4 is b square minus 2ac. Right? So this is minus 2c into a plus b into b minus root del b minus, yeah, root delta, yeah, b into b minus root delta is, yeah, by 2 plus 2b. So this is minus 2c into a plus 2b into omega f. So this belongs to if, right? So, right. So this says that so omega f square belongs to if, and this implies z omega f into if, the subset of if, and this was the ring of integer O delta. So this implies that if is an ideal of the ring of integer. Okay, so given the form, we sent it to an ideal, and we may send the binary quadratic form f to this equivalence class of if, right? Under this equivalence relation, that I is equivalent to j, under this equivalence relation, I is equivalent to j. If there is alpha beta not equal to 0, so that alpha times I equal to beta times j. So, so why this map is well defined? That is the question now we need to answer. Define. Okay, that is the question. Why this map is well defined? So suppose, so what do we have to show precisely? So suppose f is related to G, properly equivalent. So there is SL to Z matrix which takes the matrix of A to matrix of G under Q transpose A Q. Then we have to show that ideal generated by F and the ideal generated by G, there is some alpha and some beta in the ring of integer O, both are non-zero, so that alpha times IF equal to beta times IG. So by the way, if is non-zero because you can see, for example, omega x plus. So let's say if xy is this and gxy is this, ax square plus bxy plus cy square, a prime x plus b prime xy plus c prime y square. Then there exists a matrix PQRS and SL to Z such that gxy is f of px plus qy and rx plus sy, right? And the matrix of G is gamma transpose AF times gamma, where gamma is PQRS, is in SL to Z. That means PS minus, so that is PQRS are in Z. I'm just recalling for your convenience, PS minus, so small PS minus QR equal to 1. So you and A prime is nothing but AP square. So you have these formulas, and AP square plus A prime is AP square plus BPR plus CR square. B prime is 2APQ plus B into PS plus QR plus 2C into RS, and C prime is AQ square plus BQS plus CS square, right? So this is the standard thing. And omega F is minus B plus root delta by 2. And you set alpha F is omega F by A, okay? So minus B plus root delta by, so this is equal to minus B plus minus, uh, so minus B plus, okay, sorry, B square means B square minus 4AC by 2A, and you know it's a root of, similarly alpha G is omega G by A, where omega G is minus B prime plus root delta by 2. So delta equal to delta F and delta G, and they are the same, okay? So we have delta F equal to delta G equal to delta, because proper equivalence keeps the discriminant invariant. So delta, since F and G are positive definite, and recall that delta equal to delta F equal to delta G are negative integers, right? So by definition, positive definiteness, and alpha F and alpha G are, so alpha F and alpha G, B square minus 4AC is negative, so these are complex number, and this is the, we have taken the positive square root, right? So this is a complex number of the form x plus iy, where y is positive, okay? So this is called the upper half plane. Like if you draw the picture, picture maybe like this. So these are, this is x-axis, this is y-axis. If you view C as R2, and this is the iota axis, this is the you know, x-axis 1. So then this is the area where x plus iy, and this is the area. All of this is the upper half plane is this entire area where x plus iy is uh, uh, where x plus iy with y positive, okay, and not in this area, for example, okay, and for example not in this area. So so not y less than 0. So alpha is obviously root of x square plus bx plus c, which is f of x1, right? Alpha x is the root of f of x1. Similarly, alpha g is the root of g of x1, which is a prime x square plus b prime x plus c prime equal to 0. And what is f of x1? So if one, since it's an integer coefficient root, if one root is alpha f, then the other root has to be the complex conjugation. Okay, alpha f bar is the complex conjugate. Okay, complex conjugation. So complex conjugation of z going to z bar, x plus iy going to x minus I bar. So f of x1 a into x minus alpha f into x minus alpha f bar, and then fxy is just the homogenization. So a into x minus alpha f. So if this is ax square plus bx plus c, f of x1, then f of xy is ax square plus bxy plus cy square, making it the homogeneous polynomial. So that will just be x minus alpha a into x minus alpha f into y, x minus alpha bar f into y. And similarly gxy, what is the definition of gxy? It is f of px plus qy, rx plus sy. See, g was, this is the change of matrix pqrf. So so this is just, if this is the thing, then that's exactly x transpose ax. So this is equal to x transpose. So this is equal to x transpose ax, and this is x transpose q transpose a q x, right? This is the matrix. And okay, so I have denoted by gamma, so I will just call it, maybe I'll just call it q. Okay, q. Okay, so this was the gxy was this. So then gxy was is simply f of if you write down the matrix px plus qy rx plus sy, because q was pqrs, this matrix. So g of x1 will be a into p minus uh, so if you just plug in value of f, if you, so what will be g of x1? So it will be f of px plus q. So g of x1, so g of x1 equal to f of px plus q rx plus s, and which is equal to, so you plug in this formula, instead of x you put px plus q, and instead of y you put rx plus s. So you get, so in this one you put x px plus q, and instead of rx plus s, instead of y, so you get a into p, so px plus q minus alpha f into rx rx plus s, right? So rx plus s, and then you get alpha into rx plus alpha f into rx plus s. So that's exactly what you get. And here also p minus r into p minus r into alpha f. So you just take the bar here, right? Instead of alpha f, you put alpha f bar here, whatever it is. See, if you put f of px plus q here, then you get a into px plus q minus alpha f into rx plus s. So then you combine the x things, then you get p minus r into alpha f into x, and q minus s into alpha f. And similarly here, you just take the bar. That's the thing. So then, but g of x1 is alpha g, right? So g alpha g is the root of this. So g of x1 is equal to minus a prime into this root, right? So alpha g is minus will be minus q minus, um, so you write it in this form, so it will be minus of q minus S alpha F by P minus R alpha F, right? That's what is. So yeah, so omega G, yeah, so omega G by so alpha G. Yeah, and by definition alpha G, so alpha G will be from here. I'm just writing alpha G, this is the root. If you write the polynomial gx1 as this, then the root is given by this minus of x minus, you clear out the thing, so x minus of q minus s alpha f by p minus r times alpha f, and that is your alpha G. And what is alpha G? Alpha G by definition was omega G by a. See here, this is from, if you want, you can give it a name, star. So it's from star, right? Okay, so uh, from star. So alpha G, so omega G by a prime is alpha G, and alpha G is this one. So this part is from star actually. So if you like, this part is from star. And so omega G by a is, now you write down S into, uh, so you divide both sides, numerator and denominator. Here you divide both sides by a, right? So alpha f by a is omega f, and this minus changes sign. So this is minus S alpha f by a. So sorry, alpha f is omega f by a. So you multiply by a on the denominator and numerator. So you get S omega f, and the sign changes, minus qa, and then denominator remains pa minus r times omega f. Okay. So now you put this denominator as lambda, pa minus r omega f. So then lambda is not equal to 0, because this is a complex number with imaginary part non-zero, and this is an integer, so this can never be 0. So then you get lambda times omega g. So you put this guy as lambda. So you multiply a prime into s omega f minus qa, and you call this maybe some other star. Maybe you put it. Maybe I call it 1. Okay, so let's call it 1. Then lambda times ig. What is the definition of ig? Ig is the ideal generated by the quadratic form G. So this is lambda times the Z module, lambda A prime plus Z omega G, right? This was the definition of ideal generated by G. And so this is lambda times M A prime plus N times omega G, or Mn varies. This is just, I wrote down this definition. But then you can take lambda inside. So this will be nothing but M A lambda plus M A prime lambda plus N lambda omega G, where M and R in Z. So this will be, now you plug in the value of lambda. What is lambda? Pa minus r omega f, right? So this is M A prime Pa minus r omega f plus N A prime S omega f minus Qa. I'm just putting this value, S omega f minus Qa, S omega f minus Qa, right? So, so this is from 1, if you like. It's from 1. Just putting the value. So lambda prime can be taken inside. So lambda times omega g is this equation 1 I used. So this is this a prime comes out on both sides. So a prime into m times p a minus r omega f plus n times s omega f minus q a, m n and z. Now notice that PQRS is a 2 by 2 invertible matrix with integer entries. So is P minus R minus QS. This is also a 2 by 2 invertible matrix. And the inverse of this matrix is SRQP. See, this is a SL2 linear combination, P and R minus R. So here you have like P, and here you have P and you have minus R, and here you have S and minus Q. So this is a 2 by 2 invertible integer matrix, and this is a combination of AR, is a combination of A omega F, both sides. So basically the abelian group generated by this is the same as abelian group generated by A and omega F, right? So more precisely, you write M inverse equal to SRQF, then S into PA. So in particular, you can take S, M equal to S and N equal to R. Then S into PA minus R omega F plus R into S omega F minus QA. You can check. this is nothing but A into SP minus QR. Like you can just expand SPA minus SR omega F plus SR omega F minus RQA. So SR omega F cancels and you get A into SP minus RQ, and that is the same thing as A, right? And similarly, Q, you take M equal to Q and N equal to P, the second row, then you get that is equal to omega F. So this set contains A and this set contains omega F, so this set contains IF. And clearly it is a combination of A and omega F, so this is contained in IF. So that means lambda times Ig, this module, this one, lambda times Ig, all these things going on, is the same thing as A prime into M A plus N omega F, so it is A prime times IF. And A prime was non-zero because it's a primitive form. So IF and IG differs by something, which is one side it's lambda and one side it's A prime. So their equivalence classes in the class group is the same. Ideal class group is the same because they differ by non-zero element. This is your alpha, this is your beta, these are integer elements these are elements in the ring of integer and they are non-zero. And you multiply this by non-zero ideal, you get this non-zero ideal times this. So this IF and IG, these two non-zero ideals has the same ideal class in the ideal class group of the imaginary number field, Q root minus delta. So that means you start with F and G are equivalent. So here, what was the crux of the argument? This the PQRS is a SL2Z matrix, the 2 by 2 integer matrix with invertible over Z. So this map is clearly well defined. Okay, so we proved well defined. Next time we'll see injectivity and then we'll see the surjectivity. So by the way, this thing small comment is that suppose you start with q root delta, where delta is in Z and delta is less than 0. So you can massage delta in a way so that you can twist it a little bit so that the ring of integer q root delta has discriminant equal to delta. And you can either make it square free and it is equal to uh, 1 mod 4, or you can make it 4 times d, where d is 2 or 3 mod 3 2 or 3 mod 4 and d is square free. So then in the first case, if delta is 4, d is 2 or 3 mod 3 and delta is less than 0, if you start with such an imaginary quadratic field, then x square minus du square has discriminant equal to delta as a primitive and positive definite binary quadratic form. And on the other hand, if delta is 1 mod 4, and then if you consider and it is square free negative integer, then you consider this x square plus xy. So delta is negative, so 1 minus delta is positive, and 1 minus delta is divisible by 4. So this is the integral binary quadratic form. It's clearly primitive, and the discriminant is equal to delta. Okay, and it's also positive definite because of the construction that this A and C are positive, and b square minus 4ac here is also negative. So similarly here, this was the discriminant was minus, it was delta, so it was negative, and this is positive, so this was also a positive definite form. So you are starting with the imaginary quadratic field. I'm saying you get a positive definite quadratic form, which has the same discriminant as the imaginary quadratic field, and then you send that positive definite quadratic form to the ideal class and by IF. So you send it to A minus B plus root D by 2 and the abelian group generated by it, and that map is well defined and will prove injectivity and surjectivity. And in principle, there's a, if you start with any ideal that has you can have two generators, at most two generators over Z. So let's say the generator is alpha and beta, and then you send it to the abelian to the binary quadratic form whose value at xy is, if the generator is alpha beta, norm of alpha x plus beta y, and divided by norm of I. Okay, so so we'll continue next time. Thank you.